All right, welcome back, everybody. A quick note on logistics. My office hours can be hard to find. So they are in this building on the first floor in the annex. So, the main entrance that's down below there, if you were to come in that way, you would just keep on going straight past the main hallway, past the bathrooms, past this little hallway that has another entrance, and then that's the annex. And as soon as you're in the annex, it's immediately to the right. It's N175. So hopefully that helps. But office hours will be are posted on the on Canvas site. But just in case you have trouble finding the room, I wanted to make sure everybody knew. All right, so today we are going to start by talking about matrices and vectors. And if you recall from last time, we started off by saying that we had training data that we wrote as pairs of feature vectors, xi, and labels yi for I equals 1 to n. And to start off, we're thinking about classification. So the yi would be a label, say, +1 or -1. And xi, this vector of features, we write as xi1, xi2, all the way to xip for our p different features. And we say this is in RP with this fancy bold R here to indicate that there are p different entries and each one is a real number. And so xip is the pth feature of the ith sample. And so then we said we wanted to consider a linear classifier. And in particular, we wanted our to predict a label, y hat, for a sample or a feature vector, x naught. And if you recall, I'm using x naught to correspond to just a generic feature vector. When we're training, it could be one of the training feature vectors, or this could be a new sample that we want to make a prediction on that's not in our training set. And the way we do this with our linear setting is we're going to say x hat is going to be a weighted sum of our features. So we're going to have weight 1 times xi1 plus weight 2 times xi2 all the way to weight p times xip. So what we said before is that we could also have a weight vector W, and that just has all of our different weights in it, W1, W2, all the way to WP. And so this is also in RP because it is a vector of real numbers and there are p different entries in it. So now that we've got these vectors, so the feature vector and the weight vector, we can establish basically some shorthand for writing these weighted sums that we're going to be dealing with. And so last time we said there were 4 different ways we could write this. We could use these angle brackets and write this as W and X naught inside the angle bracket. The order doesn't matter, so we could also write it as X naught and W inner product. And we said we could also write this as W transpose times X naught. And we could also write it as X naught transpose times W. All of these are equivalent ways of writing this weighted sum, and we call it an inner product. So in this setting now, we are going to predict new labels for a new feature vector by taking the inner product of that feature vector with a weight vector. And what we're building towards is, of course, figuring out what is a good weight vector to use based on all of the training samples that we have. Are there any questions so far? Okay. So far, we've been forming vectors for each individual training sample and for the weight vector. But we're going to form additional vectors that go across all of our different samples as well. So we can also form a label vector. So this is y underline, and this just has the labels y1, y2, all the way to yn. So this is a vector in, most generally, it's in Rn, like when we start talking about regression or settings where the y's could be any real numbers. But for classification, we would have it be in +1 or -1, again to this n power. So this is telling us that our vector has n different entries, and each entry is either a plus or -1 in this case. Finally, we can form a feature matrix. And basically, all we're going to do is take all of the feature vectors for all of the training samples and put them together in one big construct. Okay, so this is going to be like a whole bunch of vectors concatenated together. So it's going to be a matrix in Rn by P. So this is telling us that the entries are real numbers. There are n rows and there are P columns. And so what we're going to have here in the first row is the feature vector x1 corresponding to the first training sample. Now, if you remember, when I wrote each of the xi's before, it was a column vector. But now I'm telling you I want this to be a row, so I'm going to write transpose here. So recall that when we talk about the transpose, if we have a vector x, let's say x naught, and we transpose it, then this is just x naught 1, x naught 2, all the way to x naught p, like that. Okay, so it's the same information, but we're now representing it as a row instead of a column. And so in our feature matrix, our first training feature vector, x1, we transpose it, makes it a row, and then that becomes the first row of the matrix. And then we're going to do the same thing with x2, and that becomes the second row, and we go all the way down to xn for our n different training features. Any questions about this so far? Yeah.
So are there, for the label y, for the sum, are we intending to use the xi's or the xo's? Because we have weight 1 times xi1. Are we not intending to use the xo's in this?
Oh, you know what? Thank you very much. I did mean to write xo here, so thank you. I mean, I guess in general, right, we're just taking the entries of a vector that we want to make a prediction of. So this is y hat that's being predicted on for xo. So now if I wanted to make a predicted label for an xi, then I would replace this with xi. So it's just a generic formula. But thank you very much. Yeah, that's exactly right. Okay, so in this matrix, when we talk about xij, so first of all, I'm going to call this matrix capital X. I'll try to be clear about capital versus lowercase x's on the blackboard, but if it gets confusing, let me know. So in here, xij is equal to the ith row, jth column. And also, just like we talked about last time, it is equal to the jth feature of the ith sample. So the ith row of X, of the big matrix X, is going to be equal to the P features of the ith sample. And more generally, like in this particular case, we are writing this as xi transpose, like I said over there. But for a generic matrix that doesn't necessarily, if we wanted to talk about the ith row of that matrix, we're going to use the notation capital X I comma dot. So this is indicating we're taking the ith row and then we're taking all the entries in that row. And this is the notation used by the textbook that we're using for the class. Yes?
So if X is a sample, why are we calling there like a feature X instead of a sample X?
So the whole point of the question was, why, if X is a feature, are we using X naught instead of like the training features?
I mean, like if X represents a sample and the sample has multiple features, why we are saying we predict y hat for a feature X instead of for a sample X?
So when I talk about samples versus features, I think of each one of these pairs, xi, yi, as being one training sample. And then I say for that training sample, I have p different features of that sample. So we talked last time about this problem of taking an image and determining whether the face was smiling or not. So the xi's would be different distances, say, on the face between the eye and the mouth, for instance. So each sample would correspond to a different photograph with its own label. And then for that photograph, we've got multiple different features. Does that answer your question, or maybe I misunderstood?
No, I think there's like kind of a typo.
Okay. What's
like,
the typo?
Like
Oh, for a feature vector. Sorry. Is this what you mean? Is that what you're getting at? Okay, great. All right, any other questions? Okay. And then finally, we could have the, I'll just start on a new board, the jth column of this matrix X. And when we talk about the column, it means the, in this context, value of the jth feature across all the training samples. And we are going to write it as x dot comma j. So this means we're selecting the jth row, jth column, and we're taking all of the entries across all of the rows for that column. And again, this is the notation used by our book, so hopefully that'll get reinforced. So now, with this, we can write our linear model as the following. So y hat, now with the underline, is going to be all of the predictions for all of our training samples. So this is going to be y hat 1, y hat 2, all the way to y hat n. And if we find a good learned model, then the y label vector for our training data and this predicted vector are going to be the same or very close to one another. But in general, they're not the same thing. One is coming from whoever labeled our data, and the other is the output of our model. Now we can write this as the product of this matrix X with our weight vector W. And so now what we're going to do is learn about taking the product between a matrix and a vector. But hopefully you can start to see how this is giving us a little bit of helpful shorthand. Because when we started off, we had to start with a single feature vector, and then we could make a single prediction. And now we have this handy way of compactly writing all of our training data and all of our predicted outputs for all of our samples in one compact formula. And this is going to allow us to do a lot of algorithm development and thinking about how different methods work much more easily than if we were writing out these long weighted sum equations everywhere. Okay, so next we want to look at the matrix vector product. So, like for instance, x times w. So what this means is that if we were to look at the ith entry of y hat, so the ith entry of the result of doing this product, then this is equal to the inner product of the ith row of x and this weight vector w. So when we write this matrix vector multiplication, all we're doing is n different inner products exactly like we wrote on the first board. I'm just doing them one after another and then stacking them on top of each other. So if you recall, the ith row of x was equal to this ith feature vector, xi, and then we take the inner product of that with w. So we can write then this product, y hat, which is the product of x and w, as being equal to this vector, where the first row is the inner product of x1 and w, and the second entry is x2 inner product with w, all the way to the nth entry where we have xn inner product with w. So it's just a collection of inner products. And so again, we've got this like very simple, neat, compact formula that's representing weighted sums for all of our different training samples in a very simple and easy to read way. Yes? When we use this angle notation, then we don't use the transposes, but this is equivalent to saying x1 transpose times w, x2 transpose times w, all the way to xn transpose times w. Exactly the same thing. Great question. Any other questions? So one thing that I find to be really helpful to keep in mind is this notion that dimensions must always match. It's a really simple concept, but every time I have a bug in my code, it's the first thing I check, so it's just helpful to make it explicit. So in particular, we have this expression y hat is equal to xw. And so I picture this as follows. I've got my vector of predicted labels, y hat, and the number of entries in this was n. And this is the product of a matrix X, and I just want to make this a little bit more extreme actually, so it's clear that n and p are different. So this is X, which has n rows and p columns. So this is n, and this is p. And then we multiply that by w vector, which has height p, and this was y hat. So for the matrix vector multiplication to work, the number of columns in X has to equal the number of entries in W, because we're always doing inner products of each row with W. So in order to do the weighted sum, they have to have the same number of entries. And then the product is going to have the same number of entries as the number of rows in X. Okay, maybe this sounds kind of obvious, but again, it's a very, if you're just coding and, for instance, you're getting some error about not being able to multiply two things, the first thing to always check is whether you've got your dimensions right or whether you've accidentally taken the transpose of something. Okay, so let's see. I also want to revisit this notion of transpose because I talked about it for a vector, but we can also transpose a matrix. So if X were equal to the 1, 2, 3, 4, 5, 6, so if this were our matrix X, then taking the transpose of it, X transpose, is 1, 2, 3, 4, 5, 6. So we're just sort of pivoting it. You can imagine there being this diagonal that we're pivoting around so that each row becomes a column in the transpose matrix. Okay, simple concept, but it'll be useful later. And in the lecture notes that I'm going to post online later today, there's a link to a Wikimedia file that has a really nice graphical illustration of this that I think might be useful. Okay, I also want to just mention a couple of basic facts that I think will be useful. So imagine that we've got two vectors, A, which is A1 through AP, and B, which is B1 through BP. Then if we were to write A plus B, that just means that we add up each of the entries. So A1 plus B1 all the way to AP plus BP. And if we were to talk about the norm of a vector, and specifically I mean the Euclidean norm, we would write that for this vector A, say, using these double lines on either side, and implicitly we typically mean that there's a little 2 there, and we'll talk more about alternatives to this later on and what would mean if we didn't have a 2 here. But for the most part, when you see these double lines without any number underneath it, it means the definition that I'm going to give you, which is simply that we take the inner product of A with itself, and then we compute the square root of that. And the intuition here is that if we were to think about this in 2D space, which is really the easiest space to draw in, then if we were to say, so if one axis was the A1 axis and the other axis is the A2 axis, and we plot our vector A right here, then this Euclidean norm is basically telling us the distance between that point and the origin. Okay, so there's a nice geometric meaning. And then finally, we have the outer product. And we'll talk about outer products, well, I'll just say it right now. So before, when we had an inner product, we would have A transpose B. For the outer product, we're going to have AB transpose. So remember, A now is, in this case, P by 1, and B transpose is 1 by P. And so what happens when we multiply these together is, first of all, we always have this sort of dimensionality. So what happens when we multiply these together is that the inner dimensions are going to cancel out, and the result is going to be a P by P matrix. And what's in that P by P matrix? Basically, we're going to have A1, B1, A1, B2, all the way to A1, B, P. And then we have, so basically we've got A1, the first entry of A, times the entire vector B transpose. And that gives us our first row. And then we have A2 times the entire vector B transpose. So A2, B2, A2, B1, A2, B2, A2, B, P, all the way down to A, P, B1, A, P, B2, to A, P, B, P. Okay, so basically what this is giving us is, like I said, A1 times the vector B transpose, A2 times the vector B transpose, all the way down to AP times the vector B transpose. Okay, so simple concept, but the basic thing to remember is I can take these two vectors and compute this outer product in order to form a full matrix. And this is something that we will see in a little bit. Are there any questions? Okay, if not, then I want to work out a small example that's tied to our machine learning setting. So in particular, let's say that our feature matrix X has entries 1, 2, 0, 0, 0, 3. So our first training sample has features 1, 0. Our next training sample has features 2, 0. And our final training sample has features 0 and 3. And so in this case, N, the number of training samples, is equal to 3. And P, the number of features, is equal to 2. And so X1, our first, I said this verbally, but I'll just be explicit here. X1 is 1, 0, X2 is 2, 0, and X3 is 0, 3. So we can extract that exactly from this feature matrix. Now, if the weight vector W had entries 2 and 4, then we can ask what would be the predicted predicted labels associated with these features and these weights. And to get that, we are going to do matrix vector multiplication. So in particular, if we wanted to compute y hat vector, which is xw, then the first entry of this is going to be the inner product of our first feature vector x1 and our weight vector w. And then we're going to do the same with feature 2. And then we will do the same with feature 3. Okay, so for the first entry, we're taking the inner product of this weight vector with this feature vector, which is just the weighted sums of the entries. And what do we get? 2. And what do we get when we do the inner product of the second feature vector with W? 4. And what about the final one? Sorry? 12. Yes. Excellent. Okay. Very nice. Now, this is one way that we can represent this matrix vector multiplication. Alternatively, we can say that this is equal to, what we're doing here is computing a weighted sum of the columns of X. So in particular, I've got my first column of X, which is 1, 2, 0. And I'm going to multiply that column by my first weight, which is 2. And then I've got my second column, 0, 0, 3. And I'm going to multiply that times my second weight, which is 4. And so when I'm multiplying a vector times a scalar, I just multiply that scalar times each entry in the vector. So I get 2, 4, and 0. And then I get 0, 0, and 12. And when I add these together, I get 2, 4, and 12. So both totally valid ways to think about this matrix vector multiplication. And depending on the context, one can be easier than the other or more helpful than the other. So this is really nice because there's this very clear and direct link to this notion of weighted sums of features that can feel very intuitive. And when we start talking about least squares next week, what we're going to see is that this notion is going to connect directly to notions of spans, of subspaces, and a geometric interpretation of least squares. So both are extremely helpful. Okay, any other questions? All right. Now, we've been talking about linear classifiers or fitting lines to data, or doing things with weighted sums. And this might feel a little bit restrictive to you, right? How often does your data really line up nicely with a straight line? And so I want to go through another example that highlights how, with some simple manipulations, we can do something much more powerful with a simple linear model. So in particular, let's imagine that we observe our data like this. And so I'm going to use the letter Z to correspond to an observed feature. And I'm going to say how this is connected to the features X that we've been talking about so far in just a minute. But just think about this as more like the raw data features that we observe. And then on the vertical axis, we'll have the true labels Y. And then imagine that when we do a scatter plot of our data, we see something like this. So at first, we might feel a little discouraged because if we were to say, oh, I want to try to fit a line to this data, I know right off the bat, it's not going to be very good. But it turns out that the simple linear model that we've been working with can be used to fit curves like this with relatively little effort. And so that's what we're going to work out in this example. Okay, so in particular, what we could do is we could define our feature vector xi to not just be the observed feature z, but to be something more complex. So in particular, I'm going to have the first entry be 1, the next one be zi, the next one be zi squared, and the last one be zi cubed. So I'm taking a single measurement, zi, and I'm transforming it into a vector by looking at different powers of that zi. And so now I've got a feature vector. And so now if I were to use a linear model, well, first of all, this is going to give us a feature matrix X that will look like 1, Z1, Z1 squared, Z3 squared, all the way down to 1, Zn, Zn squared, Zn, cubed. Sorry. Like that. Okay, so I have put all of my feature vectors into my feature matrix. And so now if I were to think about what my linear model is doing, so y hat for the ith sample is going to be a weighted sum of these different features in my feature vector. So I'm going to have weight 1 times 1 plus weight 2 times zi plus w3 times zi squared plus w4 times zi cubed. And so now what we see is that the linear model on the features on the x's is the same thing as a polynomial model on the z's. And the weights in the linear model are the same thing as our polynomial coefficients. So again, we're focusing on linear models here, but it's an extremely powerful tool that can do things, many things, including fitting nice polynomial fits to data. Okay. Any questions? Yeah.
So I guess we're kind of leveraging the high dimensionality of the weight vector to kind of accommodate non-linearity in data. So now we can take a scalar as our feature, but that's kind of sacrificing the capability of the linear model to handle high-dimensional data. So is there a way to account for both the non-linearity and the multivariables in the feature?
Okay, so if I understand correctly, the question is, what if I were to observe, instead of a single zi, say, for each sample, maybe the observed features are, say, 2-dimensional, 3-dimensional. What can I do? So if I were to have each zi be a vector that, let's just try to keep the writing minimal, that has entries zi1 and zi2, then I can still play a very similar trick where I could form a feature vector xi that maybe is 1, zi1, zi2, zi1 squared, zi2 squared, whoops, okay, zi1, zi2, etc., right? So I can still form polynomials of multiple variables to get these higher dimensional features explicitly. Later in the quarter, we'll talk about things like kernel methods that do this implicitly and give us a major boost in performance in a lot of different settings, but we're going to hold off on that for a few weeks. Any other questions? All right. So what we've been doing so far is talking about products between matrices and vectors, which are important. But now we're going to move on to talking about products of matrices with matrices. Okay. Now, you can find any number of sources on the internet that will show you like the recipe for computing matrix products. It's not hard. It's just a whole bunch of inner products. But I want to give you a little bit of intuition about what's happening with these products and how it relates to machine learning. And so with that in mind, I want to think about a motivating example related to recommender systems. And I mentioned this briefly when we were going through the initial slides on Tuesday. But imagine, for instance, that you very luckily ran Netflix and you've got a database of customers. So maybe Becca and Tian and Victor and Michael. And then, just I don't want this to be opaque later. And then you also have a library of different movies. So you've got Star Wars, Pride and Prejudice. What did I put? Barbie. And Halloween. And then for each person, let's imagine that we know how much they liked each of those movies. So I'm going to use the numbers in my notes so that we can do some concrete examples later on. So I've got 6, 4, 7, 5, 4, 8, 2, 6. Okay, so this is our matrix of ratings. Now, of course, in real life, we wouldn't know how much everybody likes every movie. We would only observe a subset of these entries, and we would then try to fill in the missing entries. And we are going to talk about exactly how to do that later. But in order to do that, we have to know how to multiply matrices with each other. And so for the moment, just to understand a little bit about matrix products, let's assume we've got this entire matrix. And what we're going to do is we are going to write it as the product of two matrices. So I'm calling this matrix here capital X. So we're going to write X as the product of two matrices, U and V. And in this, I'm going to have X be, like we've been doing so far, N by P. So I've got N different rows, and I've got P different columns. And I'm going to write this as the product of a matrix U that in this case has N rows. I've got to have the same number of rows as X, but only R different columns. And a matrix V that has R rows and P columns. So this is still R, and this now is P. So I've set this up in a way so that when I multiply these together, again, we can always check dimensions. And what's happening is when I'm multiplying these together, all the R dimensions are basically going to be interproducted together. And so what I'm going to be left with is a product where the number of rows is the number of rows in U, and the number of columns is the number of columns in V. And in order for this to work out, I need the number of columns in U and the number of rows in V to match up so that I can do a whole series of inner products that I'm going to describe now. Are there any questions? Oh, yeah.
So here when we're multiplying like U and V, why we like take U to be more like the like why it's like U V transpose instead of like V transpose U? Like,
I don't have any transposes here. We could represent matrices in terms of transposes, but I think that's not the easiest way to introduce the notion of matrix-matrix multiplication. So what I'm saying here is simply that X is equal to the product of U and V, and I'm going to describe what that means in more detail. Yeah. Okay. So in the context of our example, we could think of for instance, U, let's say the R columns of U being equal to the tastes profiles of R representative movie watchers. And so this could tell us, for instance, the first column of U could tell us how much a romance lover would like each of our movies. And the second column of U could tell us how much a horror lover likes each one of our movies. And then we could think about V. So the P columns of V tell us how much each of the P customers resemble the R representatives. So if I'm one of the customers here, sorry, I have to step on the thing to make the camera move. If I'm one of the customers here, then there's R numbers in here, and they're telling me how much the first one would tell me how much I'm similar to the first column of U, say the romance lover, and the second number would tell me how much I'm similar to the second column of U, say the horror lover, right? So the V is now telling me for each of our P customers, these R numbers tell us how similar we are to each of the R representative columns in U. And so in terms of the mechanics, I know we're just about at time, but I just want to not start this completely over when we resume on Tuesday. If X is equal to UV, what that means is that if I were to look at the ijth entry of X, and remember this means ith row, jth column. If I were to look at that entry of X, then this is going to be the inner product of the ith row of U with the jth column of V. So I can write this pictorially now. I'm just going to redraw it. So if I've got my matrix X here, and it is the product of U and V. And now what I want to do is I want to know if I were to choose the ith column of X and the ith row of X and the jth column of X. So if I wanted to know that entry there, then what I'm doing is I am looking at the ith row of U, which has R entries, and the jth column of V, which has R entries, and I'm computing their inner product with each other. And so as I go through this matrix and I look at different entries, say as I go through different entries in one row of X, I'm just computing the inner product of the ith row of U with different columns of J. And if I were to compute different elements along this column in X, then I'm continuing to hold this column of V fixed, and I'm just varying which inner product or which row of U I'm computing an inner product with. So this notion of inner product that we started off the day with, that was central to this notion of linear models, is also central to the notion of how we compute products of matrices with vectors, and also central to the notion of how we compute products of matrices with themselves. And next time we'll see just a little bit more on this, but please do read the notes. I think there's a little additional nuance on notation, or things are explained more than once in a way that might be helpful. So don't hesitate to look at the written notes and ask any questions you might have. Thank you very much. Okay, so what is a column of X? So we're going to write that as x dot comma j, like I mentioned before. So this is the jth column of x. And the size of it now is going to be, if x is a matrix in Rn by P, then the jth column is going to be a vector that is length n. And we can also think about this as a weighted sum of the columns of U, where the jth column of V tells us what the weights are. So this is the same as taking the full matrix V and computing the product of that matrix with the jth column of V, which we write as V dot comma J. And in the context of our running example, this is the expected tastes of our jth customer. And similarly, we can think about a row of X in terms of this matrix product and think about what that means. So in particular, we write that row xi comma dot, so ith row, and then all the entries in that row. So this is the ith row of x, and this is a vector that has p entries, but I'm going to write this as r1 by p to indicate there's only one row and p entries across that row. And we can also write this as taking that matrix V and computing the product of that matrix V with the ith row of U. And I put a transpose there to indicate that, so that my dimensions match up, right? So V, we said, was R by P, and U was originally a length R, or UI dot, the ith row of U, is a length R vector, but we transpose it, so it becomes a 1 by R vector when we transpose it, and so the product becomes a 1 by P row vector. We can also think about this as a weighted sum of the rows of V, where U, the ith row of U, is telling us the weights. And then finally, what else? Oh, and then in the context of our example, it's telling us how much we expect everybody to like the ith movie. And when I say everybody, I don't mean just on average, but I mean how much each individual customer will like the ith movie. Okay, so there's lots of ways to kind of interpret what's happening here. I also want to talk about two different ways that we can think about matrix multiplication using both the notions of inner product, which we started off the day with, and outer product, which we mentioned briefly, but I want to elaborate on a little bit. Yeah. Okay, so if I heard correctly, the question is when I write something like UI dot transpose V, do I do the transpose or do I do the transpose first or the product first?
Or do you do the transpose first, or do you take the row first?
Oh, I see. So what I mean here is I am taking the ith row of U and then oh wait, what am I doing? Yeah, I'm taking the ith. This is a good question. Let me think about this for a second. Xi, I want that entire row. So I'm going to do, oh, you know what? I think I just don't need the transpose, right? Because UI dot is just a 1 by R vector. So I think I just didn't need the transpose. Yeah, if that's what you're pointing out, well done. Very good. You got it exactly right. Thank you. Okay. So when we talk about matrix-matrix multiplication, there's a couple of ways we could do it. One is inner product representation. And this is closest to what we've been doing so far, where we write the product U times V by being U1 dot, and this is a row, U2 dot, this is a row, all the way down to UN dot, and this is a row. And then we represent V as a collection of columns, V dot 1 and V dot 2, all the way over to V dot P. And then when I compute the product, what I'm doing is I'm taking the inner product. So for the first top left entry, I'm taking the inner product of the first row and the first column. So I've got the inner product U1 dot V dot 1. And then for the next entry, I'm going to I'm in the top row, so I stay with the top row of U. So I have U1 dot again, and I'm taking the inner product of that with the second column of V, V dot 2. And I continue this all the way out till I have U1 dot. So I just keep the top row of U fixed. I'm taking inner products of it with each individual column of V, V dot P. So each column here corresponds to a different column of V. And similarly, each row here is going to correspond to a different row of U. So at the bottom here, we would have UN dot, inner product with V dot 1. Sorry, the notation's a little heavy. Inner product of UN dot with V dot 2 all the way to UN dot with V dot P. Okay, so this is the inner product representation because we're representing this product where each entry in this matrix is just an inner product of a row from the first matrix and a column from the second matrix. Another perspective on this is the outer product representation. Where I'm now going to write U and V. Instead of writing U in terms of its rows and V in terms of its columns, I'm going to represent U in terms of its columns. So I've got U dot 1, U dot 2, all the way to U dot R. Those are the columns of U. And I multiply that by the rows of V. So V1 dot, V2 dot, all the way to VR dot. Okay. So I haven't changed anything. I'm just changing I haven't changed anything meaningful. I'm just changing the way that I'm writing this, right? I can represent you as a stacked column, a set of rows, or I can represent you as concatenated columns. It's still the same matrix, so I haven't changed the content of anything, but I'm just saying if I represent the matrix in terms of its columns as opposed to its rows, it's going to give me another way of thinking about this matrix multiplication. So the first thing I want to point out is that here, when we have this inner product representation, then the number of rows of U is going to be the number of rows in the product, and the number of columns in V is the number of columns in the product, but they're not necessarily the same. When we get to the outer product representation, the number of columns in U is necessarily the number of rows of V. Both of them are R. They have to be the same number. And so now, when I write this product, this is going to be the same as a sum of different outer products. So I'm going to have the product U dot 1 times this row V1 dot and then that gets added to U dot 2 times V2 dot all the way to R. So I've got now the rth column of R, of U, times the rth row of V. So instead of representing my matrix product as a collection of n times p different inner products, I can represent it as this sum of different outer products. And so this can be useful in a number of ways. We'll see several in the context of this class. But for example, there we go. For example, in our movie example that we've been going through, we could think about this column of U. What we said was that way back on the other side, the first column of U could correspond to like the taste profile of, I don't know, the romance lover. And then this row of V could correspond to how much each customer likes romance. And then here, this one could correspond to the taste profile of the horror lover. And this is telling us, I don't know, customer affinity for horror, etc. So this has got a nice, I think, visceral interpretation in terms of, what we think about these matrices as representing. And so now what we're getting when we do these inner products is, remember, each one of these products is going to be a whole matrix with n rows and p columns. And so what we're getting is we're getting a sum of our different matrices, our different outer products, where the first matrix here, in the context of our example, is a matrix of movie ratings corresponding to the romance component of the rating. And this we can think of as a matrix of movie ratings corresponding to the horror component of the rating. And so if we want to get the full ratings matrix, we have to account for how much people like romance, how much people like horror, etc., and how well aligned each movie is with romance and horror, etc. Yes?
So you're saying these two representations are equivalent, outer product and the inner product representation?
That's right. So you can form two matrices, U and V, like in Python, and you can just use the regular matrix multiply operation in Python and get the product. And then you could simultaneously write a script that's going to compute every entry using the inner products. You'll get exactly the same quantity, same product matrix. And you can write a script that will compute the product using this sum of outer products, and it'll get exactly the same numerical values. So these are just equivalent ways of representing the exact same operation of matrix-matrix product. Yeah. Great question. Any other questions? Okay, I have one final example that I want to run through. Can you guys still see okay when I write on the light, or is it impossible to read stuff there? You can see? Okay, great. So here's a question, and I guess it's kind of an example, but also a question. So given a matrix X, what is the smallest value of R so that we can find matrices U, where X is going to be, as always, N by P, and U is going to be N by R, and V is going to be R by P. So we want to find matrices of this size, where if we compute their product, it equals X. So if we think back to this outer product representation that we had over here, I said, well, we can represent this product UV as a sum of R different outer products. And so what I'm asking now is, if I just hand you a matrix X, how many different terms in this sum do you need? How big does R need to be in order to find matrices U and V? Or if we think about it in the context of our recommender system example, it's like saying, if I give you this matrix full of all the customers' ratings, how many different representative movie watchers are represented here? Are there just two, just romance and horror and nothing else matters? Or are there, like a million unique flowers, right? Everybody's just a little bit different. And so this notion is related to the idea of matrix rank. And we're going to talk about this in a lot more detail in the coming weeks, but I just want to introduce the basic idea here. So in our example, we're going to let X be equal to 1, 2, 3, 4, 3, 6, 9, 12, 4, 8, 12, and 16. Okay, so now we can think about, can we find different matrices U and V, where if we multiply them together, we get this X. So here is option A. And I want to emphasize here, trying to take a matrix like this and figure out what the matrices U and V might be is not a trivial problem. It's not something that I would ask you to do by hand. This is just to sort of illustrate the concept here. We're going to talk about computational methods you can use to do this later in the quarter. So I figured this out offline, but it's not something that I expect you to know how to do. So one option is that we could choose U to simply be 1, 2, 3, 4, 3, 6, 9, 12, 4, 8, 12, 16, and V to be equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so now if you work out the product of this u and this v, you will get that x that I wrote there. And so in this case, the number of columns in u and the number of rows in v is equal to 3. So the question is, can we get even lower than this? Can we use even fewer columns in u? Before we say that, I just want to mention, this is a very special matrix called an identity matrix. So if we were just back in the world of scalars, if you take any number and you multiply it by 1, you just get that number back out, right? Yes?
Sorry, may I ask why we can multiply UV? Because U is 3 times 4 matrix, but V is 3 times 4.
So I would take the inner product. To multiply these two together, I would, for instance, take the inner product of the first row here with each column there.
U has 4 rows, but V only has 3 columns.
Right, so U in this example is going to be 4 by 3, and V in this setting is 3 by 3. So the product of the two is going to be 4 by 3, which is the size of x. Yeah. So this matrix here is called an identity matrix. So what it's characterized by is having ones all along the diagonal. It's a square matrix, and everything else is 0. And if I were to multiply an identity matrix times another matrix that has, so I usually would write I as for an identity matrix. So say IP is going to have P different ones, and everything else in the matrix is 0. And so now if I were to write IP and multiply it times a vector, let's say W with P entries, it's going to be W. So it's an identity because anytime I multiply it by a vector, I just get that vector back out. So an important notion to know. They're not super relevant to this problem. So when I multiply this U and V together, I get that X. I've got R equals 3 different columns. But the question is, can I get an even smaller value of R? And in this case, the answer is yes. Otherwise, it would not be a very good example. All right, so in particular, I'm going to consider option B, which has U being equal to 1, 2, 3, 4, and V being equal to 1, 3, 4. So if I were to, so this would correspond to R equals 1. I've got a U that only has 1 column. V only has 1 row. But if I compute this outer product now, I'm going to get exactly X. If I just use exactly the outer product formula that I introduced towards the beginning of class. So this is a matrix where I've got a full big matrix, but basically if we look back at this matrix, every column is a multiple of the other columns. So this column is equal to 3 times column 1. And this column here is equal to 4 times column 1. And this one, of course, is 1 times column 1. And so I'm observing that these 3 columns are all just scalar multiples of each other. And so I can write it as this outer product, which is telling me I've got this one base column, and in X, all the other columns are just scalar multiples of it. So the first column is just U, and the second column is 3 times U, and the third column is 4 times U. Okay. In the context of this class, in general, saying what's the smallest value of R that lets me factor a matrix like this is a hard problem. But if you see this is called a rank 1 matrix because R is 1, and you should be able to identify when all of the columns are just multiples of one another. That's one factorization we should be able to do. Are there any questions? Okay, so homework 1, I think, is released today, and it is due a week from Monday, so you've got approximately 10 days for it. As I said, recitations start today. Instructor office hours start next week, and I will see you all on Tuesday. Thank you very much.